Hi guys, my name is Tensor. Welcome back to the Golang blockchain tutorial series. This is video number 5 in this series. In today's video, we will be creating a wallet module for our blockchain. This wallet module will be separate from the blockchain itself, and in the next tutorial, we'll work to integrate the two together. Before we get to all that though, I do want to do a little refactoring. The main.go file is filled with all of our command line logic, and we can break it off and put it into its own module. Let's go ahead and create a folder called CLI and then a CLI.go file inside of it. Then we can cut out all the command line logic and just put it into this file. Back in the main.go file, we can reference the CLI package by bringing it in as an import and then by calling CLI.commandline. Notice that the run method is throwing back an error because it's private, so we need to make it capital. And once we've done that, everything should work properly. Let's also refactor our transaction file. Specifically, I want to refactor the TX output and TX input structures and their respective methods. We can just grab the two structures and their two methods and copy and paste them into a tx.go file inside of our blockchain package. The main purpose for doing this is for the next tutorial because we will be expanding upon all the logic for these two structs quite a bit, and so it makes sense to put them in their own file. Before we create the code for our wallet, let's first take a look at the structure of a wallet in a blockchain. So the wallet is made up of two keys, a private and a public key. The private key itself is essentially the identifier for each of the accounts inside of the blockchain. And so each private key that we generate needs to be completely random and unique from the other private keys. Otherwise, multiple users can access the same account. The public key, on the other hand, is a key that we can actually give to other users. And we use this public key to actually derive the address, which is the address that we use to send and receive data in the blockchain. So the chart would look something like this. We derive the public key from the private key, and then we derive the address from the public key. Here's what our wallet structure will look like. Now notice that for the private key, we're using a special type called ECDSA.privateKey. This ECDSA import stands for elliptical curve digital signing algorithm. And that's the algorithm that we're going to use to generate the private key as well as the public key. From a mathematical standpoint, an elliptical curve looks something like this. And actually it could also look something like this. And it could also look something like this, where we have a circle and then we have a line like that. If we go ahead and look at the private key type inside of the ECDSA library, you can see that the private key itself is a struct that has a D big integer and then a public key structure inside of it. The D big int field is a value between 0 and 2 to the 256th power, which is a rather large number, and we randomly choose this number. Then with the private key, we pick a spot on the elliptic curve, and we use this D value to then move around the curve that many times until we reach another spot. So for instance, if D is, say, 10, we would pick a spot here, and then we would pick 10 other spots randomly until we land on the 10th spot, which we would then use to put into the public key. And you can actually see this in the public key by looking at the X and Y fields, which are both big integers. These X and Y fields are that final coordinate that we landed on based on the D value. Let's go ahead and make a function which will actually create our private key and our public key. This function will be called newKeyPair. First, we need to define the type of elliptic curve that we want, and we're going to use a P256 elliptic curve. This means that the outputs from this elliptical curve will be 256 bytes. We can now use the elliptic curve along with a random number generator called a random reader to generate our private key using the ECDSA generate key function. Naturally, we also want to handle any errors that come back from this function. Now to make the public key, we use the concept of elliptic curve multiplication that we talked about before, where we're picking values on the elliptical curve at random. And we take these X and Y values, we convert them into bytes, and then we append them together using the append function and this special syntax which makes use of the varadic symbol. Normally, the append function lets us append a value into a more complex collection or type. In this case, we take the value of X as bytes, and then we explode the value of Y so that they can be concatenated together into one single value, which will make up our public key. Then finally, of course, we return these two values from this function in a tuple. The cool thing about this algorithm is that in theory we can generate up to 10 to the 77th power different keys. For reference, there are approximately 10 to the 78 and 10 to the 74th number of atoms in the known universe. So it's very unlikely that we'll generate two private keys which are exactly the same. Now that we have the ability to generate the two keys, let's create a little abstraction function which will allow us to set them into a wallet type. So we call our new key pair function, and then we take the public and private keys and put them into the wallet structure and then pass them back from this function. So we've created our private key, then we've used ECDSA to create the public key, and now we need to create the address. And as you can see, there are quite a few steps that we need to go through to create the address. Let's dissect this flowchart so that we can understand how it works. So we take the public key and we run it through a SHA-256 hashing algorithm, and then we run the result of that through a RIPE-MD160 hashing algorithm to get a value called the public key hash. We are then able to take this public key hash and pass it through a SHA-256 algorithm twice, take off the first 4 bytes of the resulting hash, and that is our checksum value. We also take the original public key hash and pass it down here as well, and then we have a version value, and we concatenate these 3 values together and then pass them through a base 58 encoder algorithm to create the address. This RIPE-MD hashing function is just a 160 byte hashing function. It's similar to the SHA-256 algorithm, except it decreases the amount of bytes that represent the value from 256 to 160. In the next few tutorials, we'll talk a lot more about what this checksum and this version are. The checksum is important for verifying and signing transactions. This version value is also something that we'll talk about further in future tutorials, but it essentially indicates where in our blockchain this address resides. If we go back into our code, we need to first get a library which gives us access to the RIPE-MD160 hashing function, and then we need to create 2 constants. One will signify the checksum length in bytes, which is 4, and then the other one will be the version, which we'll just make as a byte with a value of 0, and this is just a hexadecimal representation of 0. Now we can take the public key, pass it through the SHA-256 algorithm, and then pass it through the RIPE-MD160 algorithm to create a public key hash. So let's create a function called public key hash, which takes in the public key as a slice of bytes, and then outputs our public key hash as a slice of bytes. Remember, we first want to take the public key and pass it through the SHA-256 algorithm, so we'll do that. We can then create a hasher for the RIPE-MD160 algorithm using RIPE-MD160 new, and then we can take our public hash and write it into the hasher by calling hasher write on the public hash. Then to actually hash the public hash, we need to call hasher sum. This function normally takes a value and then concatenates it with the value that we want to write. And because we don't need to concatenate any value to the value that we're hashing, we're just going to pass in nil like that. And then of course we can just return this value from this function. We next need a way to take the public key hash and then generate our checksum. We'll take in a slice of bytes and output a slice of bytes, and we'll call this payload. We'll pass it in first to the first SHA-256 algorithm, and that will give us the first hash, which will then pass back into another SHA-256 algorithm, which will give us the second hash. And then we can take the checksum length, which is the first 4 bytes of this second hash, and return it from this function. Before moving on to create the actual address, we need to create functions which will allow us to encode and decode our hashes using the base 58 algorithm. For this, I'm going to import a third-party library, and then I'm just going to create some utility functions which wrap around this third-party library, and we'll put this into a utils.go file inside of the wallet module. Base 58 is an algorithm that was actually invented with Bitcoin. It's a derivative of the base 64 algorithm, except the main difference is that it uses 6 less characters inside of its alphabet. The characters that are missing from the base 58 algorithm are the 0 character, the capital O, the lowercase l, the capital I, and then plus and /. The main reason why these 4 were taken out is because they can easily be confused for one another. So O can easily be confused for 0 depending on the font, and then lowercase l can easily be confused for uppercase I. Because public IDs and addresses are fairly sensitive and we don't want users sending their tokens to the wrong address, we can take out these values and not have to worry about them accidentally typing in the wrong letter. With the actual encode function, we input a slice of bytes and then we output a slice of bytes. We take that input and we push it through base 58 encode, which gives us a string, and then we need to recast that string as a slice of bytes and then just return it from the function. With decode, we input a slice of bytes and we output a slice of bytes again. We have to take our slice of bytes, cast it as a string to pass it into base 58 decode, and then the resulting decode is just a slice of bytes, so we can just return it as it is. Now let's come back into our wallet.go file and create a address method on the wallet struct, which will allow us to generate an address for each of our wallets. I mentioned before that we need the version, which we have. We need the CheckSum, which we also have down here, and we need the public key hash to create this address. And as I mentioned before, we concatenate these 3 values together and then pass them through a base 58 algorithm to create the address. So first we need to get the public hash key. And so we can just call the public hash key on the wallet's public key value. Then let's take our version, put it into a slice of bytes, and append it with this public key hash by using the append function and that special syntax that we looked at before. Then from this versioned hash, we can create our checksum. So we just pass the versioned hash into the checksum, which will give us our checksum. Finally, we want to take the version hashed and again concatenate it with the checksum using the append function. And then we can pass the resulting full hash through the base 58 encode function, which gives us the address, which we'll just return from this entire method. Let's add some print statements to this function so that we can actually run it and take a look and see what the public key looks like, what the public hash looks like, and what the address looks like. Inside of our main.go file, we can now just reference the wallet module, and then we can just call wallet make wallet to make the wallet, and then call wallet address to print everything out. As you can see here, we have the public key, which is quite large. Then we have the public hash, which is quite a bit smaller. And then finally, we have the address, and you can see that this is even smaller than the public hash. So each of these have their own distinct look to them. And if we go ahead and run it again, you can see that all of these values change rather drastically. The only real commonality is the fact that the address has a 1 in front of it, and this comes from the constant version number which we're appending to all of our values. So currently on all of our addresses, they will all start with the number 1. Now that we can create the wallet key pair as well as the address, we need to add some kind of persistence to this wallet module so that the individual using this module will be able to store their public and private keys on their local computer. For the purpose of this, we're not going to use our Badger database, and that's because we want to use the Badger database exclusively for the blockchain, and it's also because the wallet module itself is separate from the blockchain module. So we can create a constant string which points towards where we want to store the wallets on our disk, and I'm just going to store them into the temp folder as a file called wallets.data. We also need to define the shape that our data will take, and I'm just going to store all of our wallets in a map where we have our key as a string, which will be our address as a string, and that will correspond with the wallet struct, which is just the public and the private key. So when a user inputs their address, they can easily fetch their wallet out by just accessing it through the map. Let's first start by creating a save file method on the wallet structure. First, we'll create a bytes buffer so that we can store all of the content that we want to save to the file. Then we're going to use our gob encoding library to actually encode the buffers into the file. And we need to register that we're using the elliptic P256 algorithm to create the actual private and public keys. We can then create the new encoder on the bytes buffer by calling gob new encoder, and then we can encode the data by calling encoder encode. And then finally, to write all of this into the file, we just call io-util write file, pass in the wallet file string, which we defined above, then pass in the bytes from our content bytes buffer, and then of course we need to give this function read and write permissions so that it can properly create the file if it doesn't already exist. Now we can create a load file method, which will load all of the wallets from our file. We need to start by checking to see if the wallet file exists or not, and if it doesn't exist, we'll get back this is not exists error, and we can check to see if our error is that type, and if it is, we'll return the error from this method. Once we've verified that the file exists, we can create a variable for our wallets. Then we can read the file. So we just read all the bytes out of the file and we put this into our file content variable. Then we basically want to do what we did down in the save file method backwards. So we register with the gob encoder that the data needs to be encoded with the elliptic P256 algorithm. And then we can create our decoder by calling gob new decoder. And of course we need to create a bytes reader first. So we'll take our file content and call bytes new reader inside of this function. And then we'll decode all of the data from the file into our wallets variable using decoder.decode. Finally, we'll take the wallets variable's wallets field and then put it into our structures field in memory. And then if we get all the way down here, that means we have no error. And so we'll just return nil from this method. Having the load file method will now allow us to create a function called create wallets, which will populate our wallets. So first we'll create the wallet structure, and then we want to make the map for the wallets field inside of our wallet structure, and then we'll load from our file, and then we'll just return our wallet structure. As I mentioned before, because the wallets field is made with a map, we can easily get an address out of it. So this will be a method on our wallet structure, and we'll just pass in the address as a string. And then we just return calling to our wallet structure with the address as the key, which will give us back the wallet that we want. We can also create a function which will allow us to get all of the addresses in our wallet structure. So we create an array of strings called addresses. Then we iterate through all of the wallets in our memory. We take each address and we append it to our addresses array of strings, and then we return it from this method. And now finally we need a way of actually adding a wallet to our wallet's memory map. So we'll call the make wallet function to build a new wallet, and then we can create the address by calling wallet address. And we need this in string format, so we use fmt sprintf to take the bytes and convert it into a string. And then we'll take the wallet, we'll put it into the wallet's map with the address as the key, and then we'll just return the address from this function. And that's all we really need to do for our wallets module for now. Before we finish off this tutorial, let's add some logic to our command line so that we can actually create a wallet as well as print out all of the wallets that exist. For our two new functions, we want to add to the usage strings. So first we'll have a create wallet functionality, and of course this doesn't need any arguments, so it'll just be create wallet. And then we have a list addresses functionality, which again doesn't need to take any arguments. Inside of our command line module, we of course want to import the wallet module. And this will then allow us to create the different functions that we need for the actual functionality that we want to add. So for list addresses, we want to call wallet create wallets to create the wallet structure. And then we can go wallets get all addresses from this wallet structure, which will give us all the addresses. And then we can iterate through all of the addresses and just print them out. Creating a single wallet is very similar to what we did up here. We create the wallet structure by calling create wallets, and then we want to add a new wallet to this wallet structure, and then we want to of course save the wallets to a file by calling wallet save file, and then we'll print out the address that was created by calling this command. Now let's come down to our run method and add 2 new flags, one for the create wallets command and then one for the list addresses command. In the switch statement, we can now add 2 new cases, and these act exactly the same as all of the other cases around them, except they call on their respective flags. Finally, we just need to add some if statements to the bottom of this method, which will check to see if these flags have been parsed. And if the create wallet command was parsed, we can just call CLI create wallet, and then if the list addresses command is parsed, we can call CLI list addresses. If you go to run your application and you find that you're having some dependency errors, go ahead and use the go get command to get the third-party libraries before we run our go run command. So here you can see we run go run main.go and our usage is now much larger. Now we can go ahead and run our create wallet command to create a wallet. And so here's what the address looks like. We can run create wallet again to create another random address, and you can see it's completely random compared to the other address. So I've created a few wallets, and now we can go ahead and run the list addresses command to list all of the addresses for these wallets. And here you can see that it just prints out all of the local addresses that are connected to our wallet module. Now, of course, we could use these addresses with all of our other blockchain functions, but they wouldn't do anything special compared to just an arbitrary string because we haven't added any logic to actually integrate the wallets with our blockchain yet. And we'll do that in the next tutorial. Alright guys, well I hope you enjoyed this tutorial. If you did, feel free to like and subscribe. If you have any questions or comments, feel free to leave them in the box below. And if you disliked this video, then by all means downvote it as much as you like. Have a good night.